Swayam Prabha. Digital India. Educated India.
Well, that's the third bala of the day, right? Anyway, I'm very, very happy to be here. And something which was missed out on yesterday's felicitation. So I would like to felicitate Professor Satyamurthy and Sugna Madam. And this is something representative from IISER Mohali. And Professor Satyamurthy would tell you more about this. This is Passiflora. It's a passion flower. Let me call it a passion flower. And I think Agastya Bhati, who is a BSMS student of IISER Mohali, again, all of us are coming from this particular institute, whose foundations were laid by Professor Satyamurthy. And there is also a scientific culture which had been built up within IISER Mohali with respect to teaching, science, and there is also a catchword to it. We always tell the students that science is a way of life and science is fun. And this is one of the problems which Professor Satyamurthy worked on. He also managed to integrate quite a few of my department colleagues. Arjit, who had sent a message yesterday, who is an ultra-fast spectroscopist, an organic chemist, Professor Ram Shastri, who is the head of the department. Okay, I think, fine. So all of them together actually worked on this particular flower. They looked at the symmetry patterns of it. They did so the reaction diffusion system to analyze the symmetries and the patterns formed, so on and so forth. So in principle, I think this is my happy birthday or a happy 75th birthday to you. Yeah. And Sugna Madam also has been a mentor to many of the students here. So today I think I will stand as a representation of the students who taught me how to do science. So I'm going to start with a movie. So I have enough time. And most of you have seen this movie. This is something which I picked up from the YouTube. It's a scientific demonstration. Well, this talk has had a lot of saddles, but I'm going to talk about something which is called a rotating saddle. Now that looks like a saddle. If you place a ball there, it's going to fall down to the points where it can fall down. But then this guy is called Alan, and he creates such kind of movies. So essentially, what he's going to do is he's going to rotate this particular saddle very, very fast. And the higher the frequency, the better it would be. So now you place a ball there, the ball simply remains on top of the saddle. So the point of it is, my rotating saddle, my rotation here is going to be performed. So this is the question which I'm going to deal with today. Can we have a quantum mechanical realization of this for electrons? Basically, the rotation of the saddle is going to be mimicked by a circularly polarized laser. The idea is, can the circularly polarized laser induce electronic deformations in certain kind of systems? And the system which I'm going to look at is also another ring. There is also another connection with Professor Satyamurthy in this particular work. I'll talk about it. So we're going to talk about benzene in a circularly polarized laser. So the idea is it's a prototypical system that I'm looking at. You take a circularly polarized laser, which is propagating perpendicular to the ring. So this is the problem. And before I really get into my talk, I would like to thank Lurdraj, Sanjay, Ashwini, and most of Professor Satyamurthy's group have been good friends. We keep meeting all the time, and it's good fun to be here. So, So let me try and explain to you what we do. So the first equation which you see is the usual Schrodinger equation. So I'm not working with a Hamiltonian which includes a quantum mechanical interaction of, there's no quantum mechanical realization of the laser. This is a semi-classical thing. And I'm looking at high intensity conditions, so it is pretty much justified that I would use a semi-classical interaction. Now here, I'm going to present something which is called the Kramer-Henneberger reference frame. So the idea is I have a single centered Coulomb potential. I have a linearly polarized laser which is on top of the Coulomb potential. So it's a dipole interaction that I'm looking at. So within this dipole interaction, with a sinusoidal oscillation of the laser, the Coulomb potential is going to do this. Now, if you have an electron which is bound inside the system, what is going to happen is at a given instant, the electron actually sees a barrier. So one possibility is that it could tunnel ionize. The other possibility is that because of the oscillations which are involved, there could be in multiples of omega, it could go over the barrier and go out of the system. But there is also another possibility here. The electron could come and reach the classical turning points which are there here. And now the direction of the electric field actually changes. So the electron could spend more time near the classical turning points. So in that case, one could think of an effective potential which looks like this. So this is a plot of a single-centered Coulomb potential. The black one is without the laser. Now, if it spends more time near the classical turning points, an effective zeroth order Hamiltonian, effective zeroth order potential would actually look like this. So the single-centered Coulomb potential is actually split into a dichotomous kind of system. So the distance between these two minima, the red curve and the blue curve, this depends on the classical quiver distance of the electron. So in principle, the laser can induce structures within the atom. And in principle, if you look at this multi-centered thing, this looks like a diatomic molecule. So an atom could look like a diatomic molecule in the presence of a linearly polarized laser. So this is some sort of an understanding that we develop. Now, here, in this particular movie, there is a movie which is running here. So, So this is helium atom. This is a result of the calculations that we do. And these are the densities, the one electron densities in the presence of a linearly polarized laser and helium atom taken. So what you notice is that there is a maximum which develops in the density near the classical turning points. So this is the fully time-dependent picture. Now, within the fully time-dependent picture, we are actually picking out a zeroth order Hamiltonian, which effectively looks dichotomous. There are also higher order time-dependent terms. But for the time being, let us forget all that, because what we want to do is we want to understand how the electrons move with the laser. So these are typically high-frequency terms. In the beginning, we are actually going to throw them out and then try and understand what happens to the system. Now, again, the same illustration. So now you have an effective potential which is dichotomous for an atom. And as you keep increasing the laser parameter, so this particular quantity alpha 0 is the classical quiver distance, which is a ratio between the amplitude epsilon 0 and a frequency square. Now, if you do an electronic structure calculation on helium atom, so these are the orbitals which are there here. These are the densities, these are the momentum densities, so on and so forth. So initially, when alpha 0 is 0, which implies that there is no laser, which is a free field case. Now you keep increasing it, the densities actually shift towards a classical turning point. So this is the zeroth order Hamiltonian, which I'm actually going to use to analyze things. Okay. So in principle, if the take-home message here is that for the zeroth order potential, the electron spends more time near the classical turning points. Now, what happens in the presence of a circularly polarized laser? Now you have the same hydrogen atom. Here, there is a 3D plot of the Coulomb potential. Even in the presence of a circularly polarized laser, it starts looking like a torus because it moves away from the center, and obviously the classical quiver radius in the case of a circularly polarized laser would imply that the electron actually spends more time within this particular torus. So every atom in the presence of a circularly polarized laser would look like this. So this is another plot. It's just a section which is taken, and this particularly depends on the laser parameters, as you can see. Now, so the question is the following. Let's take benzene. Benzene is made of 6 atoms. 6 carbon atoms are good enough. We'll forget the hydrogen atoms for the time being. Now, this is the potential which is given, and this is the free field density. So in the case of free field densities, the atoms, the densities are more near the atoms, so on and so forth, which is the usual case which we know. Now the question which you can ask is the following: if a single atom is toroidal, what is the effective potential for a 6-membered ring? Now you have 6 carbon atoms which are arranged in an equally spaced fashion as a hexagon. So this is just a schematic picture of what would happen. Now I've drawn blue circles here with a radius of 0.7. So 0.7 is actually a laser parameter which includes the intensity of light divided by the frequency square. So this places a distance parameter on the molecule. Now let's say that you keep increasing this quiver distance. There is one configuration, there is only, so this is alpha 0 equal to 1.35, the circles barely touch. You have to imagine that these circles are actually tori. So there is one, so now when you take alpha 0 equal to 1.5, which is more than the carbon-carbon bond distance, these circles start intersecting. But then, if the circle radius is equivalent to the bond distance, all circles would intersect and a deep potential is formed in the middle. So this is something which we can easily understand. So the atom looks like a tori because the potential is going to be deeper in the torus region. Now you keep increasing the radius of the torus, there is only one particular point at which all the 6 tori would intersect and you have a deep potential in the middle. So this is exactly what has been shown. So these are schematic plots of the effective potentials, not schematic plots, calculated plots. And this is the particular configuration which we are interested in. So what would this tell you? Chemistry-wise, you would think that the electrons would localize right in the middle of the ring. Now, what kind of implications does it have for a driven system? This is what we will look at. So now what we do is the following. We do field-free electronic structure calculations in the presence of this effective potential. And naturally, we actually see that the densities now start increasing in the middle of the ring. So there is also a self-repeating pattern of hexagons being arranged right here. But the deepest point, you see the Z which has been put here. So these are different density contours. So you actually see that the densities get arranged towards the middle of the ring, right? And this is going to happen for only one particular configuration. So the structure of benzene is in principle imprinted on the laser parameter. So this is going to happen only when the classical quiver distance is equivalent to the carbon-carbon bond distance. Now, we did more. We wanted to quantify the electron localization, and then we also did something which is fun. So there are 2 quantities which have been calculated. From the group of Professor Gadre, so I started looking at electrostatic potentials. So, so the electrostatic potentials also tell me that there is a negative potential right in the middle. So the electrons would come and localize in the middle of the ring. We looked at yet another quantity just to be sure, because there were reports of electron localization functions, time-dependent ones, which have been reported. So we looked at electron localization functions also, and we find evidence for the electrons being localized in the middle of the ring. Then we did something which is fun. So we thought we will just look at H plus going through benzene. So this is one particular problem which is associated with Professor Satyamurthy. In fact, the way I started was I did a summer project with somebody called Professor K.L. Sebastian. So the first project which I was actually given was, so can you put H plus inside C60? And this was yesterday shown up in the slides, a work by Shruti Maheshwari and Professor Satyamurthy. So that way also there is a connection. And later on I came to Professor Gadre. We started looking at electrostatic potentials, protons interacting with molecular systems, so on and so forth. But what I want, the take-home thing which I want to show you is, without the field, there is a barrier, very large barrier for the proton to go through benzene and come to the other side. But if you look at this particular configuration in which you have the circularly polarized laser counter-propagating to a plane of benzene, there is a dip right in the middle. The barrier completely disappears, which is what you expect. If you have electron localization in the middle of the ring, where would the proton go? It will go to the middle. But then, obviously, it will shuttle through. It could shuttle through. So you have a well right in the middle of the ring. So this is the interaction of the proton with benzene in that particular effective potential which is given. So where all the 6 rings, which are atom-centered, intersect. Now, we didn't stop it there. Alpha 0 is an adiabatic parameter. Those are laser parameters which are experimentally controllable. So we looked at mean field orbitals in this effective potential just to understand what is the kind of electronic rearrangement that happens. So basically, this is within the Hartree-Fock level, a time-independent calculation. As alpha 0 is an adiabatic parameter, so obviously when you have avoided crossings, there is going to be a mixing of the orbitals at that particular point, and the mechanism of how the electrons get towards the middle of the ring is qualitatively described by the particular set of avoided crossings that you see. So there are multiple states which are involved. We also done an analysis by taking the particle on a ring problem and superimposing it onto the orbitals of benzene, which makes sense because the angular momentum imparted by the circularly polarized light is similar to something which is like the particle on a ring. So there are a lot of pictures with respect to that, but I'm not going to show those. But finally, how do you experimentally realize these states? And luckily, Peter actually set the stage for me. These are results of calculations from an in-house developed package. We don't do the dynamics within the effective potential. We do the time-dependent electronic dynamics within the usual length gauge. All the analysis was done with the effective potentials. The prediction was done with the effective potentials. But finally, we have actually calculated it in the lab frame. So the first question which we asked is, what is the lifetime of those middle of the ring electrons in such a kind of state which will come up? The alpha 0 parameter is something like a ratio between the intensity and the frequency. So obviously what we have done is we have also varied the frequency and tried to come up with laser parameters, different kind of laser parameters for the same alpha 0, which is a distance parameter which comes out of benzene, from the structure of benzene. Now, if you look at harmonic generation spectra, when alpha 0 is 1.35, this is when the electrons are not in the middle of the ring. This is when the electrons are touching, so the harmonics that you get is up to 30. But when you take alpha 0 to 2.70, where you have electrons in the middle of the ring, the harmonics which actually come out is double the number of it. So this is actually a balance between, if you want to come up with a semi-classical explanation for this, it's a balance between the counter-motive force and the ionization potential, so on and so forth. So you have to also understand something, in the sense that if I'm going to increase alpha 0 further, the rings will never intersect. There's only one particular configuration at which these rings intersect. So there could be, this is, in principle, this could be something which is most efficient for harmonic generations in the case of benzene. But there are also other problems to it, in the sense that we have kept the nuclei frozen. One would assume that it's difficult to align benzene. Such a kind of gas phase experiment may not be possible. You have to also take into consideration that there are vibrations of benzene which would actually increase the width of these particular, each of the harmonic generation spectra, so on and so forth. But a natural thing is to think about a circularly polarized laser which propagates perpendicular to a surface of graphene. Graphene is made of a lot of benzene rings. And this same effect of all 6 rings intersecting right in the middle would also be there for graphene. So we have effective potentials for graphene, but we have not yet done calculations on those. So this is the idea that we actually thought about. And this work was done by Mishu, Prashant, Maitreyi, and me. Well, Mishu did the analysis of the densities. Prashant here was instrumental in writing our TT prime flow case state time-dependent code for electronic dynamics. And yeah, so a couple of others made this particular picture because they were interested in graphics. And thank you. That's all that I have to say.
Swayam Prabha. Digital India. Educated India.